I'd now like to introduce our moderator, Amy Merkel. Amy is a LASP scientist and the lead for the Office of Communications and Outreach. Amy?
Dr. Pilewskie joined the University of Colorado in 2004 with an appointment as a senior researcher at the Laboratory for Atmospheric and Space Physics, as well as a teaching faculty member for the Department of Atmospheric and Oceanic Sciences at the university. Prior to joining CU, he spent 15 years at the NASA Ames Research Center, where his work centered on airborne measurements of atmospheric radiation. Dr. Pilewskie is a well-respected expert in the field of atmospheric science. He was awarded the NASA Exceptional Scientific Achievement Medal, the Humboldt Research Award from Alexander von Humboldt Foundation. He is a fellow of the American Meteorological Society and is president of the International Radiation Commission. Dr. Pilewskie currently teaches radiative transfer, remote sensing, atmospheric physics, and instrumentation to undergraduate and graduate students at the University of Colorado. He is an assistant director of science at LASP and is conducting research on the Earth's radiative energy budget, remote sensing of clouds and aerosols, and atmospheric radiative transfer. Dr. Pilewskie is the principal investigation for the Libera mission, which is the topic of this webinar. NASA selected the Libera instrument back in February of this year as an innovative approach to maintaining the 40-year data record of measuring the radiative balance between the solar radiation entering the Earth's atmosphere and the amount that is absorbed, reflected, or emitted back into space. Thank you, Dr. Pilewskie, for joining us this evening. I'll now turn the webinar over to you.
Thanks a lot, Amy. There is the title that Amy just gave, New Earth Climate Measurements from Space, the Libera mission. Oh, let's see. I can't see my own title with this thing. Let's see that. I'm sorry. There it is. So Libera, you pronounce it Libera. The stress is on the first syllable and a short I. This is the first NASA Earth Venture Continuity mission. This was a new line of missions that was started in what's called the 2017 Decadal Survey. It's done every decade, as the title suggests, to provide guidance from the National Academy of Sciences for how NASA should conduct its business, where they should put their priorities. And this new line was put together to ensure that we maintain our continuity measurements, things like Earth radiation budget, which is what Libera is directed to, or, for example, solar irradiance, which you heard about last week, I believe, or not last week, but last month from Gary Rotman. Libera is named for the daughter of Ceres in ancient Roman mythology, and a little bit later you'll hopefully understand the connection there, but I'll leave you hanging for a moment. What it will measure is the reflected solar and emitted terrestrial radiative energy, and it'll gather those measurements from the entire globe once a day. Now, what do we mean by, so reflected solar, that means solar radiation from the sun reflected off of Earth, and then emitted terrestrial means the Earth emission, mostly in the infrared part of the spectrum, which we'll cover in a moment here. This will fly on the NASA and NOAA Joint Polar Satellite System 3 in 2027, and it's scheduled to be a 5-year mission. Our partners, our technical partners, are Ball Aerospace and NIST Boulder. So we really have, this is really a Boulder-centric mission. And also the Space Dynamics Lab at Utah State University. We have science co-investigators from, in addition to LASP at the University of Colorado, also CERES at the University of Colorado, JPL, Colorado State, University of Arizona and Michigan, and the Lawrence Berkeley Lab. So this is what I'm going to talk about this evening. I'm going to give some basics of electromagnetic radiation, laws of emission, and you'll see what I mean by that in a moment. I'm going to say a little bit about the atmospheric greenhouse effect. It's almost impossible to give a talk like this without doing that. I'm going to talk about the importance of understanding the Earth's radiative energy budget. I'm going to talk about energy balance and energy imbalance and the significance of both of those. Then I'll get into a little bit about the history of these measurements from space. And incidentally, we've been doing these for about 7 decades now. I'm going to talk about the innovations that we bring to these measurements and as we start the 8th decade of these measurements, and a little bit about our science goals and objectives. So this is a slide that I want to try to explain some of the fundamentals of emission of radiation, of radiative energy from matter, by matter. All matter emits radiative energy in the form of waves, electromagnetic waves, or light waves. Some of those waves we can see if they're in the visible part of the spectrum. That's shown here. Between 0.4 and 0.7 microns. A micron is 1/millionth of a meter. So that's the length of the wave from peak to peak, crest to crest, if you will. But what this figure is showing is the relative emission from the sun, shown here on the left. Let me change to my laser pointer here. Okay, so this is emission from the sun, and this is emission from the Earth, if the sun and Earth were ideal emitters of radiation. And for our purposes tonight, we're going to say that they're close enough to ideal. So, and the emission from these bodies follows strict laws of physics, which is dependent only upon the temperature. Okay, 6,000 Kelvin for the sun, 288 Kelvin for the Earth. If you don't like that scale, you probably should. You should learn to love it, because Kelvin doesn't go below 0. A Kelvin is always positive. Temperature is the average kinetic energy of matter. So to have a negative temperature is almost nonsensical. So that's why we like Kelvin. But nevertheless, if you're a Fahrenheit person, 288 is about 59 degrees Fahrenheit, and 6,000 Kelvin is about 10,000 Fahrenheit. But nevertheless, there's the emission from these bodies follow these strict laws, which state, first of all, that the distribution of radiative energy with wavelength, and that's what this is showing. This says radiation intensity as it changes as a function of wavelength. That radiative energy is determined solely by the temperature of the body, okay? And so we see a lot of radiation from the sun, not nearly as much from the Earth. This scale is broken, by the way, so the sun peaks emission in the mid-visible, the Earth way out in the infrared at around 10 microns is where the peak of Earth radiation is, if the Earth's temperature is 288 Kelvin. But this fundamental law says that all you need to know is the temperature of this body. This also means that you can go backwards, measure the radiation, and infer the temperature. And that's a very important, the consequences of that are very important. We're going to talk about in a moment here. But here's what else this figure tells us. It's hotter objects, at least compared to colder, radiate more energy with peak radiation at shorter wavelengths. So the total energy given by the sun and the Earth here is really the area under these curves. They don't look terribly different, except if you look at the scale for sun's radiation is about 10 million times greater than that for Earth. So there's about 10 million, the sun is radiating about 10 million times the radiation as the Earth. And also the peak of the sun's radiation, we said if it's hotter, the peak is at shorter wavelengths. So the peak of the sun is out here at wavelengths that we can see in the visible, and in Earth, much longer wavelengths. Okay, so we know what governs the amount of radiation and how it varies over the spectrum based on those fundamental laws. Now we want to really look at what is going on here, what we're measuring. So here's the sun, incoming solar radiation in these big yellow arrows. We've got reflected solar radiation in these little arrows. Our instruments, Libera, on Libera will measure that reflected solar radiation. The Earth is meanwhile emitting its own radiation. Again, it's composed of matter that emits radiation. That's given by these red arrows. That's what we will also be measuring. It's only sunlit on half of the Earth. It's radiating over the entire surface of the Earth. So now we want to consider radiation balance. And this is important. Radiation balance is important because radiation is virtually the only way that energy is transferred from sun to Earth. It's most of the energy transferred from sun to Earth is via this light. And it's the only way that Earth loses energy to space is through its radiation in these little red arrows. If the amount of this solar radiation that's absorbed is equaled by the amount of these little red arrows that's emitted by the Earth, then we say that the radiation is in balance and the Earth's temperature will remain constant if it's in balance. If energy in equals energy out, it's in balance, temperature remains constant. Again, it's only the absorbed solar radiation that matters. If Earth were a mirror, there would be no solar energy, no solar radiative energy transferred to the Earth, and it would be as if the sun didn't exist really, but it does. It absorbs quite a bit of this solar radiation. That absorbed solar radiation, you can determine that by the amount that's incident with these long yellow lines minus the little yellow lines, little yellow arrows coming out. So incident minus reflected. We can introduce a definition, something we call albedo, which is the ratio of the amount reflected, little yellow arrows, divided by the incident, which is the incoming. And that's a fraction. It's some number between 0 and 1. If it's 0, that means all of the, it means none of the incoming solar radiation is reflected. If it's 1, it's all of it is reflected. So the fraction absorbed is simply 1 minus that fraction. Okay, so incoming solar radiation is either reflected by the Earth or absorbed by the Earth. So we can calculate solar or absorbed solar radiation by 1 minus the albedo, the fraction absorbed, times the incident solar. Why do we care about that? Well, we want to put that back into this equation here. And so in equilibrium, we can determine the Earth's infrared, the Earth's emitted radiation directly from its albedo in equilibrium. In equilibrium, if we measured these red arrows, they would equal exactly this amount here, 1 minus the albedo times the incident solar radiation. And the interesting thing is, remember I just talked about those fundamentals of radiation. Temperature determines the amount of radiation. We can go backwards, measure the radiation, and we can infer a temperature. We could assign a temperature to the Earth based on this value, assuming the Earth was a perfect emitter. So that's why I drew this little infrared gun here pointed at the Earth, giving its temperature. That's kind of what we're doing here. And I think most of us here have had one of these guns pointed to our forehead a few hundred times over the last 8 months, right? So Earth's albedo is about 0.3. Its equilibrium emission temperature is about 255 Kelvin or 0 degrees Fahrenheit. So what the heck is this temperature that we're inferring here? Is it the surface temperature? Definitely not. The average surface temperature of the Earth is far greater than 0 degrees Fahrenheit, and lucky for us that it is. So we call it an equilibrium emission temperature. Really, it's nothing but what a perfect emitter would emit if it absorbed this much radiation. It's really nothing more than that. Sometimes what we say, though, is that it's the temperature that the Earth would have if it didn't have an atmosphere. That's okay. The only problem with that I have is that the albedo of the Earth, if it didn't have an atmosphere, would not be 0.3. It would be closer to 0.1. The Earth is pretty dark. It gets brighter. It has an albedo as high as 0.3 because of clouds and because of the atmosphere. Nevertheless, let's stick with that definition that this temperature that we can infer by measuring infrared radiation is the temperature of the Earth without an atmosphere. So now I'd like to introduce what I call this Goldilocks tale, or something called climate divergence. Those are the three of the inner planets, three planets that are in many ways very similar to one another, in other ways very different. And we all know our favorite one here is the one on the left, with apologies to my planetary friends in LASP. Earth, Mars, and Venus. So let's talk about these temperatures. So this top row here, sunlight received compared to Earth. So Earth receives 1 unit of sunlight. It reflects 0.3 of that. We said its albedo was 0.3. So 0.3 of that 1 is reflected to space. The temperature without an atmosphere, we said, would be 255 Kelvin, or 0 degrees Fahrenheit. What's the actual surface temperature? 288 Kelvin, 59 Fahrenheit. I think that's a little bit higher now since I made this slide. It's maybe closer to 289, but let's not quibble. Venus receives almost twice as much sunlight as Earth does. Mars receives only a little less than a half of the amount of sunlight that Earth does. Fraction of sunlight reflected by Venus, a whopping 77%, more than double the reflectance of Earth. Mars, pretty low, 0.17. Now here is where, if we were live, I would ask the audience for this question: the temperature of Venus without an atmosphere. And I usually can certainly get students to make mistakes on this one. Intuitively, they think it's very high. You've got twice as much sunlight. They know that Venus is hot, but oops, wait a second. This temperature that you'd infer if you measured Venus's infrared radiation would only be 230 Kelvin, minus 45 Fahrenheit. Mars is 216 Kelvin, minus 71 Fahrenheit. Surface temperature of Venus, though, 700 Kelvin, 800 Fahrenheit. Mars 216 and minus 71. What have we done here? What is the meaning of these numbers? Here's one meaning. The difference between these two is a measure of what we call the greenhouse effect. Okay, and here's Goldilocks. Here's the temperature that was just right. Again, we'd be much worse off if the temperature were 0 Fahrenheit. But we've got a relatively moderate 59 degrees average surface temperature of the Earth. Venus way too hot, Mars way too cold. So that's the Goldilocks tale of climate. The atmospheric greenhouse effect. And by the way, the greenhouse effect is a very, very good thing. Too much of it, however, is not a good thing. So what is the greenhouse effect? I like to define it this way. This is really the only definition you'll ever need. The surface of the Earth is warmer than it would be in the absence of an atmosphere because it receives radiative energy from two sources, the sun and the atmosphere. The atmosphere, we receive radiative energy from the atmosphere. We sure do. Remember, we said matter emits. The atmosphere, made of matter, made of molecules, emits radiation to the surface. That warms us. So the atmosphere is important for the warming of the surface, not for the reasons you typically hear. It acts as a blanket. It definitely doesn't. The blanket warms you because it suppresses convection. So the atmosphere certainly doesn't do that. The atmosphere doesn't trap radiation, nor does it trap heat. There's no such thing as trapped radiation. How much of these amounts? Here's where I would ask you also to guess. And first of all, let's look at some measurements. Let's look at some real data. This is measured solar and infrared radiation. This is at the Skywatch Observatory. This was when this observatory was at Duane Physics, on the roof of Duane Physics on the main campus. Now the Skywatch Observatory is on an East Campus, still maintained as it was when these measurements were taken by Scott Kittleman of ATOC. But this is a measure of solar radiation as it varies. This is a daily average of solar radiation as it varies over the years. You can see it peaking in June. Now, these units, I'm going to talk about these units in a second here. These are watts per square meter. This is the unit. A watt is power, energy per time. So watts per meter squared is a power density. That's the downward solar radiation at the surface. There's the terrestrial or infrared radiation in red. And you can see here that it's greater than solar radiation for most of the year. And it also doesn't make these big excursions going from high to low values. Those excursions from high to low values are from clouds. As you all know, clouds reduce the amount of sunlight reaching the surface. Actually, infrared radiation is anti-correlated. Clouds enhance the greenhouse effect. They provide more infrared radiation at the surface. So usually clouds will imply more radiation to the surface. What do the averages look like? I'm just going to focus, there's all the seasonal averages. I'm just going to focus on these annual averages. 190 watts per square meter from the sun at the surface in Boulder, 309 watts per square meter from the atmosphere. So a heck of a lot more infrared radiation. So there it is. That is the greenhouse effect. Globally, those numbers changed. We're pretty close to the global average for our sunlight in Boulder, about 188 watts per square meter. We have less infrared than global average, and we can explain that. That's almost certainly attributed to clouds. Boulder has less cloud cover than many climatological regions in the mid latitudes. I just want to put this here. This is something I stole from my colleague Tom Woods several years ago, although I give it different value. The visible light from a candle spaced every 1 square meter would be about 0.04 watts per square meter. That's the visible light. That's not other thermal energy released from the candle, but just its visible light. So if you're interested, so 25 candles in a square meter would give you 1 watt per square meter. This is a global radiative energy budget. These types of cartoons are fairly common. They tell us how energy comes in at the top of the atmosphere, is distributed through the atmosphere by absorption in the atmosphere and scattering and reflection from the surface. I just wanted to show you the global numbers compared to what we showed in Boulder. So here's the 188 watts per square meter coming to the surface. 165 is absorbed and 23 are reflected. And here's the infrared 345. That's why I showed this chart. I also want to show that, in fact, here's the measurements that we're making. So we're already, LASP, University of Colorado LASP is already measuring the incoming solar radiation. Again, if you saw Gary's talk last month, this is currently with the TSIS mission, but we measured this incoming radiation with the SOURCE mission for 17 years. We're currently measuring the outgoing reflected solar radiation with CERES, but we will with Libera by the end of this decade, and the outgoing long wave or terrestrial radiation also with CERES now, later on with Libera. I also point out here, this chart also says that there's an imbalance, that globally averaged over long periods of time, there's actually an imbalance at the top of the atmosphere and at the surface. We don't have that equilibrium state that I suggested or that I posed a few slides ago. The significance of that is that we're pretty sure that climate is changing. We're certain that climate is changing, and it's this imbalance that is responsible for that climate change. I'm not going to say a whole lot more about climate change, other than saying that it's reflected in this imbalance. So there's how much of each. Boulder, 63% more infrared than solar. Globally, there's about 80% more infrared radiation reaching the ground than solar radiation. That's over the entire globe. So those are averaged over the globe, over long periods of time when we talk about balance. But if we look at smaller scales, certainly smaller time scales, but also spatial scales, there are very important imbalances that really determine our the global circulation. Um, so what this figure shows is the top of the atmosphere net radiation. By net radiation, that means radiation coming in minus radiation going out. And again, that's both solar and infrared. There's only solar coming in, there's infrared going out. This is as a function of latitude. So here's the equator. Um, and these are the tropical regions between 30 south and 30 north. And then here's the poles up here at 90 north. And what this says is that at the equator, in the tropics, we have a surplus. We have more energy coming in than going out. At the poles, we have more going out than coming in. The consequence of that is a poleward transfer of energy through the atmosphere and through the ocean. That, along with the rotation of Earth, sets up this circulation pattern that gives us easterly winds in the tropics. That easterly means from west to east, from east to west. I'm sorry. Westerlies are west to east in the mid latitudes, both in the northern and southern hemisphere, and then easterlies again at the poles. These are the large scale cells of rising and sinking motion in the various latitude bands given here. So this is very important. And again, these are the sort of things that we're going to measure. So I wanted to talk a little bit about history. We are going to get in the queue over for what I said is now a 7-decade-long record of measurements from space. It started with the Explorer missions in the late 1950s and followed on by the Tyros in the early 60s. By the end of the 60s, the Nimbus missions began, Nimbus 3 in 1969. And then in the 1970s, Nimbus 7 started in the late 70s in 1978. The interesting thing is that Nimbus 7 had a whole bunch of other Earth viewing instruments on, in addition to those measuring Earth radiation budget. All of these other ones have Earth radiation budgets, but Nimbus 7 had ozone measurements. It had total ozone mapping instrument. It had a microwave radiometer, stratospheric and mesospheric sounder, limb infrared monitoring of the stratosphere limbs, and a coastal zone color scanner. So really, we think of 1978 as the start of Earth measurements from space and Earth remote sensing from space. But we actually were doing radiative energy budget measurements almost 2 decades before that. This is a great picture of Vern Sumi, the father of satellite meteorology, with one of these early Explorer satellites, Explorer 7, in the late 1950s. I like to say here, where's the bunny suit? If you've been to other of these LASP public lectures, you've probably seen pictures of LASP engineers and scientists wearing bunny suits and working on instruments in the clean room. But back in the 1950s, you could get a lot closer and hands-on with these instruments. A great picture here. This is one example. This is the infrared instrument on Explorer. Vern is probably working on the solar instrument over here, which is essentially a black plate. This is a white plate, but sensitive in the infrared, so reflecting all solar radiation, but absorbing infrared radiation. The black plate absorbs all solar radiation, and you measure the temperature change. This is a spin stabilized satellite. So this is spinning around this axis here, and on occasion these things scan over the Earth and view the Earth. Even these very early, what we now would call primitive instruments, we learned a heck of a lot about the Earth and its radiative energy budget. This is from a paper by Tom van der Haar and Vern Sumi, published in the 1960s about these very first measurements. they found that 40% more energy must be transferred poleward by the atmosphere and ocean circulations. I showed you that imbalance with latitude of the incoming and outgoing solar radiation. 40% more energy transported. That's a heck of a lot of energy. That changed our whole understanding of the Earth's atmospheric circulation. And the Earth was a warmer and darker planet than previously believed. What do we mean by that? Well, the Nimbus 3, which came in the late 1960s, it confirmed those earlier satellite measurements. These dots you see here, these were by our best pre-satellite era understandings of, in the top panel, the outgoing long wave radiation. If you didn't like watts per square meter, you're going to hate this. This is calories per centimeter squared per minute. But doesn't matter. This just shows you that you've got more outgoing long wave radiation where it's warmer. And then this is albedo shown here in the bottom panel, varying with latitude. And here, these are it was considered that the Earth was a much darker planet, had a much brighter planet, had a much higher albedo than was determined by these earlier measurements and then verified by Nimbus 3. I wanted to take a moment to say a little bit about these estimates of Earth's albedo. All of these values up until 1957 were pre-satellite era. Satellite era established the albedo of the Earth to be around 0.3. First, I want to show that there was one value here that got pretty darn close by Danjon in France. He was an astronomer who measured the dark and bright sides of the moon and made those comparisons to get the albedo of the Earth. And how can you do that? Well, the dark side of the moon isn't completely dark. It's actually illuminated by the Earth, which can be measured and used to determine its value. So that was actually pretty remarkable. But then I wanted to show this value here by Julie London in the late 1950s. Julie London was at New York University at the time that he did that work, but in the early 60s, he came to the University of Colorado, where he spent the rest of his career. I believe he was there at the start of what that time was called the Department of Astrogeophysics. It's now the Astrophysical and Planetary Sciences Department. He was the chair of that department for a few years in the 1960s. But one of our own and one of the giants in Earth radiation budget, particularly in the pre-satellite era. This is his diagram. Remember, I showed you that other cartoon. This is his version of how that radiative energy is coming into and out of the atmosphere. And Julie London, one of the greats and one of our own. Okay, back to the history. Following the Nimbus 7 came the IRBI mission in the 1980s, lasted till 1990. The primary instrument, which was the scanner, there was a non-scanning instrument that lasted well throughout the 90s. I don't know if it made it all the way to the year 2000, but it lasted much longer. The IRBI also confirmed the earlier results. And so now we have 3 missions that obtain nearly the same global and zonal average of Earth radiation budget values. And again, confirmed, again, what we learned at the very start, that there had to be 40% more poleward energy transport than thought from pre-satellite era estimates. I also wanted to say that Nimbus 7 and IRBI also measured total solar irradiance. Nimbus 7 was our first measure of total solar irradiance. I assume this is a figure that you saw from Gary Rotman last month. This shows the record of total solar radiance, including the modern, or the most modern era, which for now 17 years, LASP has been making, first with SOURCE, started here in red, and now carried on with TSIS here in yellow. And These measurements from LASP, the source mission especially, was instrumental in changing our understanding of solar radiance. All of these other values were recalibrated in response to the measurements from source. Source revolutionized the solar radiation measurements from space in a way that we hope with Libera will also revolutionize the Earth radiation budgets measurements. So now we get to CERES. Cloud. What does CERES stand for? Clouds and Earth's Radiative Energy System. These are the measurements, the most modern measurements we make of Earth radiation budget. They started in the year 2000. Now you know the origin of our name, Libera. Libera is the daughter of CERES. It's not an acronym. We chose it to represent the continuing on of these measurements that have been going on since 2000. There are currently 6 instruments still flying right now, but 5 of those 6 instruments are beyond their nominal 5-year lifetime, and we estimate that by the latter part of this decade, there's going to be a 50% probability that we have a gap in this record, and that's not good. I have an example to show you why it's not good. There was an intended follow-on called the Radiation Budget Instrument. It was started development in 2014, but that was canceled in 2018. And so that's why NASA competed this mission, this Earth Venture Continuity mission, to which we applied and were selected. So this is more from CERES. This shows you on the left here is the reflected solar radiation in watts per meter squared. It's kind of hard to read those numbers, but take my word for it that brighter means more reflectance, and you can tell you've seen these types of this type of imagery from other satellite images. In the visible, bright means high reflectance. In the infrared, bright means low emission. And really what that tells you, again, we can go back, this means temperature. A lot of these bright regions on the infrared are correlated with bright regions in the solar, and that's because clouds are higher in the atmosphere. Some are very high, especially around the tropics, reaching very high altitudes, and therefore very cold. Colder they are, the less radiation that they emit to space. So that's the correlation between those two. By the way, I want to say here that I hope we get a chance to get a science on a sphere to put in the lobby of one of our buildings at LASP and show our data, show Libera data, very much like what you see here. That would be pretty cool. What else have we learned from CERES? Well, we've learned that clouds cool the Earth. This was actually learned first from the IRBI mission in the 1980s, but was verified from CERES. They cool the planet, and here I'm going to refer to cooling again in terms of watts per meter squared by about 20 watts per meter squared. With clouds, we have 20 watts per meter squared more leaving the planet, therefore cooling, than we would without clouds. So that was a very important observation. That's a global average. What you see here is the global distribution, and what's chiefly responsible for this are these are almost semi-permanent stratus layers, low-level clouds, pretty thick, bright clouds off the coast of California, off the coast of South America. The North Atlantic storm tracks also responsible for this general global cooling due to clouds. CERES tracks changes in short and long wave radiation. What you see here, these are called flux anomalies. This red line refers to the long wave radiation or terrestrial radiation. The blue line is solar radiation. By anomaly, we mean difference from the average over, in this case, a 17 or 18-year period of CERES measurements. These are plotted along with what we call the ENSO index, the El Nino Southern Oscillation Index. If that index is highly positive, those are El Nino years. highly negative are La Nina years. Interestingly enough, from about 2000 all the way through the first decade and into almost up to 2014, the global average surface temperatures didn't change much. It's what we call the hiatus, where they didn't change that much. Since 2014, they've started to abruptly rise again. And coincidentally or not, probably not, but we don't fully understand the cause yet, but we see pretty large changes, especially in the shortwave radiation. This is less shortwave radiation going out to space. That actually means a warming that due to decrease of reflected shortwave radiation. So these are the sort of things that become very important, establishing these long-term records and understanding how climate changes. This is kind of interesting and emphasizes the need for continuity. These, let me just show here before I show that, this dotted curve here, this is the IRBI measurements, the scanner measurements that ended in around 1990. CERES started up in 2000. If you look at the mean, these change, by the way, annually, fairly dramatically. I'm sorry, this is albedo that we're plotting, okay? So albedo changes kind of dramatically here over a year, but then there's an abrupt change. If we look at the difference between the mean from IRBI and the mean from CERES, it's 3 watts per meter, or I'm sorry, in terms of albedo, it's 1/100th. Then you say, well, that's not that big, is it? Well, if you converted that to watts per meter squared, you get 3 watts per meter squared. For reference, the change due to greenhouse gas warming in net radiation at the top of the atmosphere is around 2.6 watts per meter squared. So this change is bigger than the change due to greenhouse gas perturbations of atmospheric radiation at the top of the atmosphere. This is bigger than that 2.5 century change. So this is almost certainly not real, but the problem is that we really can't tell, and we can't it's difficult to bring these into alignment because of this gap here. So this is something that we'd like to avoid. Make sure the Libera gets launched in time to connect to CERES. So now let's come up to our mission, Libera. We continue the measurements started by Explorer and Tyros and Nimbus 3 in the 60s, Nimbus 7 in the 70s, IRBI in the 80s and 90s, and then CERES 2000 to present. What do we bring to the table? Why were we selected? Well, we have some very important innovations. Number one is higher accuracy from electrical substitution radiometers using vertically aligned carbon nanotubes. Now that's a mouthful. What do we mean by that? Well, again, remember those black plates we showed you, how he was measuring these in the 1950s. I'm getting a, let me know if my audio's here. I just got a network instability message. I'll kill my video if I have to. So you have something black that's going to absorb radiation. You can measure the electrical substitution. Instead of measuring temperature, we keep that plate, so to speak, we keep it at a constant temperature. We supply electrical power to stabilize the temperature. When it absorbs radiation, we reduce the electrical power to keep it at the same constant temperature. That reduction in electrical power it tells us how much radiative power we had absorbed by that black substance. And so that's why it's called an electrical substitution radiometer. It allows us to make exquisitely accurate and precise measurements. And then vertically aligned black carbon nanotubes, that's about the blackest substance that you can get. And so these are new instruments built with our collaborators at NIST in town. And these are really state-of-the-art. We have one flying in space now on a CubeSat measuring spectral irradiance. And these are, like I said, these are really state-of-the-art. we have another measurement. Instead of measuring, we measure all of the solar radiation that's reflected. We have another instrument that measures just half of that. Why half of it? Well, we split the total energy in half that's coming from the sun. But that where we split it also separates where the solar radiation is absorbed in the atmosphere and from where it isn't absorbed. We know from experience, from our eyes, that there's very little absorption of sunlight in the visible. That's why we can see through the atmosphere. Just beyond the visible, though, in the near infrared, water starts to absorb. Having that extra measurement tells us a lot about where energy is deposited into the atmosphere, what's doing the absorbing, helps us to better understand changes that we see. And then we also have a wide field of view camera. This is very important because part of what we want to do is to simplify how we make these measurements in the future. Right now, we depend on data from a very complex imager that tells us a lot about the scene context, what we're seeing in terms of cloud amount, but even more than that, it tells us about the state of the atmosphere. But we're trying to do something that can simplify that, so that when we make these measurements in the future, we don't have to be on this big bus like JPSS to make our radiation budget instrument measurements. We can do them on smaller platforms, maybe even CubeSats in the future, maybe constellations of CubeSats. So that was our forward thinking in proposing this mission. I just wanted to show, there was a couple articles in New York Times, one about this, about black carbon to begin with. This was published in just a year ago today. It was published in New York Times. And this is about the work being done at NIST to create these black substrates. They absorb 99.99%, even more than that, of incident light. This is the blackest stuff known. Interestingly enough, New York Times is really obsessed with very black absorbing things, because they published in just July of this year, ultra black fish in the deepest seas. These are now the blackest natural occurring, the pigments on these fish are the blackest natural occurring substances that are known, actually approaching those carbon nanotubes. So pretty kind of fascinating. This is our instrument. I'll go over this very quickly here. There we have 4 telescopes measuring shortwave, long wave, the split shortwave, and then one what we call a total channel, which has no filter, that collects light from all wavelengths. You can't see all 4 telescopes because this is a sun shield here in the side. There's that wide field of view camera I mentioned. This is a scan mechanism. This rotates about an axis, almost parallel to this arrow here. This scans from limb to limb on the Earth. We also can scan about the azimuth shown here, through an axis that's perpendicular through this plate here, to be able to scan the Earth in different ways. Science objectives, in the interest of time, I'll go over this very briefly. One thing is, our primary objective is to continue these measurements. There's a lot of science in having longer data records of how this energy budget is changing over time. And so we have a lot of science objectives related to that. And this will help us to understand the processes responsible for changes in energy flow. And it helps us to constrain models, climate models. By having this longer data record. And I will say longer, and hopefully, I think if everything goes to our plans, also more accurate. Self-contained, innovative, affordable. Part of that is not needing this complex imager, something simpler like this wide field of view camera. And then the third thing is understanding better how this solar energy is deposited in the Earth system, either deposited at the surface, absorbed in the atmosphere through water vapor, through condensed water in clouds, and on and on. I'll move on. This is a summary. We're going to measure shortwave scattered and emitted long-wave radiances at climate quality levels of accuracy, precision, and stability. Maintain and continue this ERB Earth Radiation Budget Climate Record. Demonstrate a pathway towards sustainable, reproducible, innovative observational approach to enhance science, reduce cost and risk of gap for future measurements, enable technology infusion to enhance the capabilities of future climate observing system, and advance our understanding of the Earth climate system with novel research and analysis. I hope in the not too distant future to be able to talk to you about the findings from Libera. Very quickly here, this is our Libera science team. I just wanted to point out there is Tom Vanderhaar, who was a student of Vern Sumies at the University of Wisconsin in the early 1960s, who wrote the paper from which I quoted that showed those remarkable first discoveries from ERB measurements from space. It's great to have somebody connected to the very first measurements that we've made. There's some great scientists on this team. Here is our entire LASP Libera team, including all of these folks listed here, along with our scientists listed here. I'm going to leave this here for you to find people that you know. I'm just going to point out two people with whom I am tied, intimately tied. We talk probably several times daily. The first is Brian Boyle, our LASP program manager, and then Dave Harbour. He is our brilliant instrument scientist who, along with collaborators at NIST, are the inventors of this really incredible new way of measuring Earth radiation from space. So thank you very much for your attention. And
thank you, Peter, very much. I'm going to clap for everybody. That was wonderful. If anybody has any questions, if you could please type them into the Q&A now. Peter, I have a question. Maybe I missed it, but when is the launch date?
2027.
2027.
So a little while, but delivery of instruments in 2025.
And then will a follow-on mission that you were talking about before, would a proposal for that be before launch or?
That is a great question. So this person here, Odell Coddington, is the principal investigator of what we call an incubator proposal, which is already the next generation Earth radiation budget instrument. So, at LASP, we're always thinking ahead. We've already got a new generation started before we've even gotten this one up in space. But what this instrument does is provides greater spatial resolution. I didn't say anything about spatial resolution, which means it's the smallest thing on the Earth that can be resolved by our measurements. For Libera, it's going to be on the order of 20 meters. So, that's pretty big. And but it's okay for climate missions, but there's a lot that we can do with higher resolution. Odell and her team, which by the way also includes Dave Harbour and collaborators at NIST, but they're developing this instrument that's a detector array that will measure to resolution as high as 1 kilometer. Someday, maybe that's the next generation, we'll make it a 2-dimensional array, and in the other dimension, we'll be able to separate radiation into different wavelength bands, because there's so much we can do with that information, having different wavelengths. So will we propose that? I mean, I'll tell you one thing, we're pretty sure that we'll propose a flight of this new instrument before the Libera mission flies. That's usually in a demonstration mode, but we're definitely thinking ahead.
Okay, so we have a couple more questions. There's a question that says, or asked, that you said that the energy in and energy out imbalance has been observed for a long time. How long?
Did I say observed for a long time? That was a mistake by me if I said that. The well, okay, it depends. It depends which imbalance we're talking about. If it's that global averaged imbalance of 0.6 watts per square meter, I have to tell you that that has never been directly measured. It is the solar radiation measurements that we make are accurate enough to determine that imbalance. The Earth radiation budget measurements that we make are not accurate enough to determine that quantity. So we really have to rely on some other measurements and some modeling to come up with that value. So that's not really, excuse me, been measured. What has been that latitudinal imbalance though was known that tells us poleward energy transport of energy. That's been known since, again, the first measurements that we made from space, which is in the late 1950s.
Right. Somebody wants to know if there's any more technology development that needs to happen before Libera launches, or is the technology development already been done?
Well, now there is some, and it's mostly related to the detector itself. And again, this is with our collaborators at NIST. They grow these carbon nanotubes because they're only about a nanometer in width, but they're aligned vertically. They're grown at very high temperatures, and remember, we've got to measure the temperature of these things, and so they're put on a substrate that acts as the temperature measurement device, a thermistor. And there's a question of the fidelity of that thermistor under these very high temperatures, and so the process is we've got prototypes made. We've got some development to do to arrive at the space qualified detectors. We're not there yet. It'll take some time, but we're confident that this approach is going to work. We have some fallbacks that are going to be almost just as accurate. If we don't, they will still use carbon nanotubes, by the way. So I didn't give you the details of the difference between just any old carbon nanotube and vertically aligned carbon nanotubes, but that's an important distinction.
There's a question of, will there be any portions of the Earth that this observation system will not observe?
No, we should see the entire Earth during any given day. There'll be little strips that will be left out, but no, we'll be able to monitor the entire Earth. It's a polar orbit with a satellite, and we scan from limb to limb.
And then we have another question that quoting, you mentioned the wide field of view camera will simplify the radiometer measurements of Libera and potentially future missions. How so? Well,
for one thing, it's a lot simpler instrument than these what I called complex imagers, most notably MODIS and VIIRS. If you're familiar with those, they make measurements at many different wavelengths over both solar channels and infrared channels, and they're very, very important instruments in providing information for our understanding of climate processes. So they're very important. But right now, the way that this data from CERES is processed, it requires that data to do its own data processing, and to go through those details. I'll spare you those details. It's rather complicated, one of the issues is that to derive the energetically important quantities, see, we're measuring in a single direction. To derive the energetically important quantities, we really have to know the radiation coming from all directions. And so we do that by means of what's called an angular distribution model. Now, what that means is that tells us if we make a measurement, say, from this type of surface with this much clouds and this much water in the atmosphere and on, that if we measure this amount of radiation in the direction that we're looking, we can then use this model to tell us the direction of radiation in all other directions. And then we can derive this, what I call the energetically important quantity. We need that imager to help us do that. We're going to try to do something similar with a far simpler instrument that basically measures radiation coming from all different directions instantaneously. Now, that by itself isn't enough to be able to do all that CERES does. But again, looking toward the future, and we're flying with a VIIRS instrument, so we will be able to do the same type of processing that CERES does now. In the future, though, yeah, we can fly with a simple camera like this, but we can also fly with something we call a hyperspectral imager, an imager that's even more complex than CERES, than MODIS or VIIRS, but also in a decade's time will be available in a much smaller package. So, the future of these measurements, I'm sure, are going to be simpler, less costly, smaller packages, meaning they can go on smaller launch vehicles. But I think it's very likely that they're going to be better as well. So the point is that we'll hopefully avoid the risk of having breaks in these measurements and then having uncertainty in Earth climate because of that. Sorry for that long-winded answer.
Okay, so we're just going to do one more question. Is it possible to stitch the data sets together from the multiple imagers that you discussed, CERES, Libera, future missions, etc., to monitor the climatological change in net radiation at the top of the atmosphere?
Yeah, that's right. Yes, and that's one of our goals. Now, we'll do all that we can to put the data sets on a common calibration scale, like you saw. Well, I didn't show. So I showed the solar irradiance measurements on their native calibration scales. It just so happens that several of those made in the last decade or two rescaled their calibrations based on the source measurements. But we go one step further and put all of them on a common calibration scale. And it's important, we require overlap of those different measurements to be able to do that. Our hope is that we have that overlap with CERES and then beyond there, and yeah, that we have a continuous record. It's not all, I have to be a little bit cautious though, that it's not, we'll do the best we can. Some aspects of these measurements, for example, the complicated data processing that goes on, particularly with the CERES data, might not make it simple for us to put them on a common scale. It's a great question. It's a pretty complex answer, but we're going to do the best that we can, and hopefully, yeah, we do that, and we'll know more then about multi-decadal climate and climate change. A season or a year does not a climate make, and a decade barely does it either. Really need to know how things change over long periods, longer than a decade.
All right, well, I think we'll end with that. Thank you very, very much